Thank you for waiting. So, okay, to start with, what is authenticated encryption, AE? AE is a symmetric key crypto system to provide privacy and authenticity simultaneously. And it is widely deployed in real-world protocols such as TLS and WPA. AE has two functions, encryption function and decryption function. Encryption function takes nonce, associated data AD, and plaintext as input. Here, AD, associated data, is the data that is not encrypted but authenticated. An encryption function output ciphertext and tag. Decryption function takes nonce, AD, ciphertext, and tag as input, and then output decrypted message when these inputs are authentic. Otherwise, output error message bot. Okay. AE is so useful scheme, but when using it, there are some rules we must follow. For example, nonce respecting and decryption respecting. Nonce respecting means that the user cannot input the same nonce twice in the encryption function. Decryption respecting means that decryption function is not allowed to output other than error message bot if inputs are not authentic. If breaking those rules, so when misusing AE, privacy or authenticity of AE can be broken. For example, GCM reveals its authentication key when nonces are misused. In fact, there are some real-world attacks caused by the misuse of AE. For example, Bok et al. Investigate the real-world cases in TLS that use GCM in nonce misuse setting. They show that several TLS implementations are vulnerable to forgery attacks, and also show that more than 17,000 servers are also potentially vulnerable due to the use of GCM with random nonce of short length. The famous padding oracle attack would be the typical example of the attack caused by the decryption misuse, because in the padding oracle attack, decryption function leaks the information on the decrypted plaintext. Also, EFL attack can also be seen as the attack caused by the decryption misuse, because the mail server decrypts maliciously manipulated ciphertext and execute the code inside without verification. Okay, from that situation, cryptographers discussed misuse security of AE. For example, for nonce misuse security, two notions proposed. One is nonce misuse resistance, NMR, and the other one is nonce misuse resilience. We call it NML. In NMR, NMR is the possible strongest security notion under nonce misuse. In NMR, no matter how much nonces are misused, privacy or authenticity is maintained. NML is the relaxation of NMR. So in NML, even if some nonces are misused, privacy or authenticity is maintained as long as new non-misused nonce are used. Okay, on these two notions of nonce misuse security, there is a trade-off between security strength and efficiency. As I mentioned earlier, NML is weaker notion than NMR. However, NMR secure AE is at most rate half, while NML secure AE can be rate 1. Here, rate is the measurement of AE efficiency. It is defined as the processing blocks per one block cipher call. So we can say that NML secure AE can be twice as efficient as NMR secure AE. Okay, for decryption misuse security, we focus on this security notion: security under release of unverified plaintext. We call it wrap security. In wrap security, decryption function output decrypted plaintext regardless of verification. For privacy notion, plaintext awareness PO1 and PO2 are proposed, and for authenticity notion, integrity under wrap, int-wrap notion is proposed. Based on these misuse security notions, misuse security of AE have been extensively studied. In fact, in the previous AE competitions like CISA competition or NIST lightweight cryptography, misuse security is one of the central topics as shown in the slide. And however, here I would like to ask, what about misuse security of the standard AEs? Borone and Baiza show a comprehensive NMR comparison of third candidates of CSER plus GCM and CCM NIST standards. However, we found that there is a room for deep analysis such as NML and wrap security. We believe that it is important to clarify misuse security of standards since they are literally standard and should be the baseline of other AE. In our research, we pick up 4 standards: GCM, CCM, OCB3, and CHACHA-Poly. GCM and CCM are NIST standards, and OCB3 and CHACHA-Poly are RFC standards. They are a very, very famous scheme and widely deployed. Okay, as a result of our research, we found there are some missing or questionable cases on GCM, CCM, and OCB3. These tables show the previous misuse analysis on these standard AEs. Check means there exists security proof, and cross means there exists an efficient attack, so not providing sufficient security level. We can see that the misuse analysis of CHACHA-Poly are done, but this is not the case regarding other 3 standard AEs. We also show that we can prove security in all these missing or questionable cases. Okay, let's look into each scheme case. For GCM, interrupt security was unknown despite GCM has been extensively studied. Originally, GCM was considered vulnerable in any misuse scenario other than NML privacy. However, our results show that this is not the case, so GCM has interrupt security. Okay, next, for OCB3, Ashu et al. Proposed NML privacy attack and NML authenticity attack against OCB1. OCB1 is the previous version of OCB3. And they also claim that they focus on OCB1, however, their results extend to all versions of OCB, including OCB3. However, we show that their attacks are not applicable to OCB3, and we can prove both security. But note that AD needs to be empty for NML auth security. Okay, next. For CCM, surprisingly, only few works on probable security exist. And previous research only revealed trivial cases such as PA1 insecurity or NMR privacy insecurity. Then in this talk, we give details of these results. Okay, this is CCM. CCM is MAC-then encryption style AE, and this one is MAC-BART CBC MAC, and this is the encryption part, counter mode part. In CCM, CBC MAC output here is XORed with encryption of nonce and index 0. And also, input of CBC MAC here, B, is an encoded string derived from nonce, AD, and plaintext. I will skip the details of this B because it will be most involved part of specification of CCM. But the important thing is B is prefix-free. This prefix-free means that there is no B corresponding to the prefix of other B. This is the important thing. Okay, this is specification of CCM. Okay, regarding existing misuse security analysis, Fook et al. And Voltone and Weiser proposed NMR authenticity attack. And its complexity is 2 to the n over 2, where n is block size. Other than these results, as far as we investigated, there is no result on misuse security of CCM. Okay, let's look into our results. We first focus on misuse authenticity on CCM. We show that CCM has NMR plus interrupt security because NMR interrupt implies all missing misuse authenticity on CCM. To define this security notion, we use separated syntax instead of the standard syntax. We use an ordinary encryption function, but we newly define 2 functions, unverified decryption function and verification function. Unverified decryption function takes the same input as the standard decryption function, but output decrypted plaintext, regardless of verification. Verification function takes the same input as well, but output bit inputs are whether inputs are authentic or not. Based on this syntax, NMR interrupt security is defined as the probability of forging under encryption, unverified decryption, and verification queries. In encryption query, nonce can be repeated because it is NMR security. Okay, this is the proof overview. In the proof, we reduce NMR interrupt security of CCM to a variant of UFCMA game of CBC MAC. UFCMA is the security game for Mac, and which stands for unforgeability under chosen message attacks. As a variant of UFCMA, we define UFCMA plus game. It is UFCMA game with additional access to this part, counter mode part. Why we do that is because CBC MAC has been proven to be secure if the input is prefix-free. And recall that CBC MAC input in CCM, B, is prefix-free, and this holds even if nonce misuse. So we can get intuition that we can prove the security of CBC MAC here under UFCMA plus game as well. And then we prove UFCMA plus game of CBC MAC by age coefficient technique. We set bad event as a collision at every block cipher input. And we show that CCM has NMR interrupt security of this bound. N is the block size and tau is the tag length. This bound is the same security level as the standard authenticity of CCM. Okay, this is the authenticity result, and next we focus on the misuse privacy on CCM. We have proved CCM has NMR authenticity, but CCM doesn't have NMR privacy, so it's not balanced. Because the encryption function of CCM is just counter mode, So the same nonces produce the same key streams. So what about NML privacy, not NMR? NML privacy is defined as the probability of distinguishing encryption function from random oracle with nonce respecting queries. But the adversary can also perform nonce repeating queries to actual encryption function. I will skip the details of the proof, but we can prove that CCM has NML privacy of 2 to the n over 2. The intuition is here. In the counter mode, even if some nonces are misused, the adversary cannot violate the security of the key stream derived from other non-misused nonces. Okay. As an additional contribution, we proposed CCM2, which is the optimization of CCM. CCM2 omits the mask generation for the tag in CCM here. Therefore, CCM2 can reduce one block cipher call and also achieves the same misuse security as CCM. Thanks to this, we can expect good performance for very short input cases on CCM. This table shows that the number of block cipher calls required to process 128-bit plaintext and its parallelizability. In parallelizability, for example, 2 plus 1 means that the first 2 block cipher call are in parallel, followed by 1 block cipher call. Armunga et al. Show that general purpose AE require at least 3 block cipher calls to process non-empty input, like COFB. CCM2 achieves this minimum number 3, which implies excellent performance for very short inputs, notably on microcontrollers. Okay, before we conclude, this is the lessons learned from our research. Okay, when using AE, please check its rules and follow them. And of course, using misuse-resistant AE is also a good choice, but note that there is a trade-off relationship between the security strength and efficiency. Therefore, it is important to select AE that are suitable to your environment and check what happens if the rules of these AE are violated. So if you consider using GCM, CCM, OCB3, or Chachapoly, please check the summary table in our research. To conclude, we provided a comprehensive overview on the misuse security of these standard AEs. Among them, we found that CCM and CCM2 have the strongest misuse security. That's all. Thank you very much for listening.
Thank you so much, Akiko. That was really, really interesting. We have our pre-recorded section that we're going to start playing now, and then we'll circle back to do a Q&A. If anyone has any questions, we'll have 10 minutes at the end for you to answer questions.
Okay.
All right, cool. Thank you, everyone.
Hello, everyone. I'm Kuntong Li from Shandong University. Today, I'm very happy to share our work with you. The topic is meet-in-the-middle attack on primitives with binary matrix linear layer. This is the disclaimer. This presentation will focus on the following parts. First, the background and the preliminary of this work are given. Then we introduce our proposed new models for linear layer with binary matrix. Then the result of applying the new models to different algorithms are presented. Finally, a conclusion. the middle is a powerful cryptanalysis strategy, first proposed by Diffie and Hellman to attack double DES. The core idea is to identify two disjoint neutral sites of unknown values. Then the whole computation path can be divided into two independent chunks, which are determined by two neutral sites and donated by forward chunk and backward chunk, respectively. At last, the two chunks will meet at a common internal state where the consistence is checked to filter out candidate assignments of unknown values. In recent years, this technique is not only used for key recovery but also widely used in pre-image and Clurian attacks. Despite being clear that MITM attack is entirely determined by its characteristic, it's still complicated and error-prone to explore the whole configuration space. Recently, automated tools were introduced to find the best characteristic by solving an optimization problem. At Eurocrypt 2021, Ball et al. Proposed MLP-based MITM pre-image attack on AES-like hash function. At Crypto 2021, Dong et al. Extended the automatic model into key recovery and Clurian attacks, and introduced a table-based method to solve the nonlinear constraints imposed on neutral sites. At Crypto 2022, Ball et al. Considered the MITM attack in a view of superposition states and bidirectional attribute propagation such that neutral sites are treated independently and can impose constraints in both computation passes. So now we provide an overview of how the MITM attack framework is constructed and how it is included into the MLP language with specified configurations for the pre-image and key recovery attack as shown. Sinc and Sk are the starting states where there are lambda b neutral bytes for forward computation donated by blue cell, and there are lambda r neutral bytes for backward computation donated by red cell. After imposing LB constraints on lambda b forward neutral bytes through a feed-forward mechanism or querying a public encryption-decryption oracle, red cells can be propagated to the matching points and are independent of the blue cells. The degree of freedom for the blue neutral space is computed by this. Similarly, backward neutral bytes are imposed on LR constraints to cancel the effect of red cell in the forward computation. The DOF of the red neutral space can be computed by this formula. And B can be derived by blue cells. Instead of requiring the full states, the partial matching exploits the filtering ability derived by the deterministic relation NB等于NR. With the configuration of these parameters, the basic attack procedure goes as follows. First, choose constants in these parameters. Second, for DOFB values of blue cell, compute the NB and store them in a table. Third, for DOFR values of red cell, compute the NR and store them in another table. First, find the match between L1 and L2. Finally, for the surviving pairs that pass the match, check for a full state match. Then we give the complexity analysis. The total time complexity is this formula. The total memory complexity is this formula. Apparently, MITM characteristic is valid if and only if this formula mean DOFB, DOFR, DOM greater than or equal to 1. We can include the type of each byte with a pair of Boolean variables as follows. Then a valid MITM characteristic is defined as a solution solved by the off-the-shelf MLP solvers like Groby. Then we recall two enhanced techniques to improve the power of MITM attack. The first one is the table-based method to solving the nonlinear constraints. There are many practice MITM characteristics with nonlinear constraints, neutral bytes, which cannot be solved efficiently, and the efficiency can be improved through this technology. Another one is superposition states and bidirection attribute propagation to preserving more valid solutions. That is, in intermediate states are separated into two superposition states, and superposition states are handled independently in linear operation and can be propagated equally in bidirections. And superposition states are combined before the next nonlinear operation. Then we introduce our proposed new models for linear layer with binary matrix. To simulate the MITM attributes propagation through the linear layer, Bao et al. Proposed the MC rule for the MDS matrix in AES-like hashing, as shown in Figure A. Each input cell has an effect on all output cells in MDS matrix. However, some primitives adopt a binary matrix in the diffusion layer where each output cell is computed by the XOR of partial input cells, as the Midori's binary matrix shown in Figure B. The first output cell is only related to the last three input cells. Apparently, this will lead to inaccurate propagation if we apply the MC rule for MDS matrix on binary matrix directly, since one output cell is not related to all input cells. An alternative strategy is to apply the XOR rule for two input XOR consecutively. This strategy is valid but may miss some valid patterns by introducing additionally auxiliary variables. We take the attribute propagation through Midori's diffusion layer to state this fact. As shown in Figure A, only 3 propagations can be happen. However, with the NXOR model in Figure B, additional propagation is available. In the following, we show how to convert the propagation of red cells through the NXOR operation under superposition states into MLP language. All coloring patterns can be specified by the following set of rules donated by NXOR rule. The rule for blue cell can be obtained in a similar way by exchanging blue cell and red cell since they are dual. Then we introduce three Boolean indicator variables. The rule can be converted into a system of inequalities shown as follows. We also observe that the NXOR model may lead to some subtle inaccuracies. We still take a possible propagation of Midori's diffusion layer as an example to state this fact. A particularly explicit case is that the constraints on the same neutral cells may be double-countered due to the independent computation of each output cell, as shown in Figure A. Besides, there are some more implicit cases leading to inaccuracy, as shown in Figure B. The model's details won't be given here. Then we give the detailed results of applying the new models to different algorithms. For Midori 64, this is the round function of the algorithm and the binary matrix of its linear layer. We present an 11-round MITM-K recovery attack on Midori 64. For weakened camellia, this is the round function of the algorithm and the binary matrix of its linear layer. We find a valid configuration of the pseudo pre-image MITM attack on 14-round weakened camellia MMO. For area, this is the round function of the algorithm and the binary matrix of its linear layer. We find a valid configuration of the pseudo pre-image MITM attack on 6-round area DM. And finally, a conclusion. Our results are also summarized in Table 1 and Table 2. In summary, our work proposed the XOR model to simulate the XOR operation with an arbitrary number of input cells. Our work introduced another check model to determine the exact DOF's consumption of MITM attributes propagation to eliminate the subtle inaccuracies caused by an XOR model. Our work leading to some improved MITM attack on Midori, camellia, and area. The limitation is the size of the check model is still limited by the number of input cells n and doesn't work well when n greater than 4 in this paper. Thank you all.